In mathematics, a zero, also sometimes called a root, of a real, complex or generally vector-valued function f is a member x of the domain of f such that f vanishes at x, that is, x is a solution of the equation f equals 0. In other words, a zero of a function is an input value that produces an output of 0. A root of a polynomial is a zero of the associated polynomial function. The fundamental theorem of algebra shows that any non-zero polynomial has a number of roots at most equal to its degree, and that the number of roots and the degree are equal when one considers the complex roots counted with their multiplicities. For example, the polynomial f of degree 2, defined by has the two roots 2 and 3, since if the function maps real numbers to real numbers, its zeros are the x-coordinates of the points where its graph meets the x-axis. An alternative name for such a point in this context is an x-intercept. Solution of an equation. Every equation in the unknown x may easily be rewritten as f equals 0 by regrouping all terms in the left-hand side. It follows that the solutions of such an equation are exactly the zeros of the function f. In other words, zero of a function is a phrase denoting a solution of the equation obtained by equating the function to 0. And the study of zeros of functions is exactly the same as the study of solutions of equations. Polynomial roots. Every real polynomial of odd degree has an odd number of real roots. Likewise, a real polynomial of even degree must have an even number of real roots. Consequently, real odd polynomials must have at least one real root, whereas even polynomials may have none. This principle can be proven by reference to the intermediate value theorem. Since polynomial functions are continuous, the function value must cross 0 in the process of changing from negative to positive or vice versa. Fundamental theorem of algebra. The fundamental theorem of algebra states that every polynomial of degree n has n complex roots, counted with their multiplicities. The non-real roots of polynomials with real coefficients come in conjugate pairs. Vieta's formulas relate the coefficients of a polynomial to sums and products of its roots. Computing roots. Computing roots of functions, for example polynomial functions, frequently requires the use of specialized or approximation techniques. However, some polynomial functions, including all those of degree no greater than 4, can have all their roots expressed algebraically in terms of their coefficients. Zero set. In topology and other areas of mathematics, the zero set of a real-valued function f xr is the subset of x. Zero sets are important in many areas of mathematics. One area of particular importance is algebraic geometry, where the first definition of an algebraic variety is through zero sets. For instance, for each set S of polynomials in K, x1, xn, one defines the zero locus Z to be the set of points in and on which the functions in S simultaneously vanish. That is to say, then a subset V of n is called an affine algebraic set if V equals Z for some S. These affine algebraic sets are the fundamental building blocks of algebraic geometry.